Okay, can we continue? Is there any questions about this so far? Any questions about this, people? Can you hear me? People, can you hear me?
Yes, doctor.
Okay, thank you. So we have this matrix 6 by 6 composed of these elements and these elements. Each one, we have to be careful because of the position. And what we can do is we can apply now this transformation. We can apply this transformation for not only for the displacement, but also for the external forces. So we can apply local to global transformation to displacements and external forces, because both are vectors. So we say, originally, this is what we had. So we say this is equal to T times F. And this is equal to T times the vector in the local reference system. So we can say that F, okay, we take this to the right-hand side. Since it's in the left to the position with respect to the vector, we put it also on the left of this part. This is the inverse, and it's multiplied by K in the local reference system of the element. And then we have this T multiplied by D in the local, in the global. I'm sorry, this is wrong. This is wrong. This is wrong. This is wrong. Sorry. Okay. This operation produces, because of the special characteristic of the transformation matrix, is equal to the transpose. This is K, this is T, and this is D. There. And all of this, in the same ways as before, we call it K. So this is the stiffness matrix in the global reference system. Okay, it's exactly the same procedure, but now what we have to worry is about 3 degrees of freedom for every joint. So if we have, I don't know, 20 joints, we're going to have 60 degrees of freedom. Okay? And remember, we're working only in the plane. When we generalize these things and we start working in the space, each joint can move with linear displacements in the X, Y, and Z directions. But also, each joint can rotate in the X, Y, and Z direction. So we're going to have 6 degrees of freedom for every joint. Okay, that's why we have to be very careful with the number of joints or the size of the elements, because then the number of operations that we need to solve, it increases dramatically. And at a time, that's why we need more and more computer power, because the number of operations is so large. Okay. Let me complete this explanation saying that in the same way as before, apply boundary conditions that supports and solve in two subsystems. I think there was the word apply here. Okay. In the first subsystem, you solve for the unknown displacements. And after completing that step, you have all displacement known. You multiply by the big K matrix, and then you will have the external forces, the supports, that's the reactions. Okay? Then, for every element, you calculate the displacement in its local reference system. Okay, and you do this using the matrix T. That matrix T, remember, that's different for every element because the theta angle is different. And finally, you can calculate strains, stresses, and internal forces in the local reference system for every element. Okay, so that's the rest is standard. Any question, people? Any questions about this? No. Okay, let me, I'm going to change files. I'm going to present the example that you have in your PDF, okay? I posted last night the next homework, and there are two problems. One of the problems is, it's similar to the problem that we solved in class. We have two beams with different inertia. So I'm asking you to, but I'm including not only a moment, but also an external a force in the central section. And I'm asking you to solve that using analytic procedure. That's something that you did in solid mechanics, so that shouldn't take too much. You have to be careful with the algebra, that's all, but the rest is standard. And then you find elements. And let's see what you say about that. Okay, that's the first. And the second one is a problem related to this material. Okay, so it's an example. I'm giving you the reference there. It's a publication by Snamey. And what they do is they consider the analysis of one reinforcement in the bottom. Okay, but it's connected to a vertical stiffener of a bulkhead. So you have some elements which are in the horizontal direction, in the forward direction of the ship, and there is another element which is connected in the vertical direction. Okay, and they employ that report was developed some 40 years ago, maybe 50 years ago. It's very old. So they apply a different method. I think it was I don't remember the name of the method. I learned that here at the university a long time ago. But now we have finite elements, and you'll see if it's possible or not. Okay, so let's review this example. And Can you see my example in PowerPoint, people?
Yes, doctor.
Okay, thanks. Okay, so this is something that we did, and this is something that you need to do now. In this case, this point here has a force, and so that's something that you need to solve. It's something that we did. In this case, what I do is I apply this process in order to solve without rearranging the system of equations. And yeah, that's a solution. And then we go for every element. Okay, in this case, I don't have to transform this into global because this is the same. But I can apply this polynomial interpolation for each one of the joints. So, and this is the result. And you see that on the left, it's clamped, and you see that this is basically horizontal. On the right, is simply supported, you see the rotation. Okay. That's for the internal forces. Remember, shear force for every element is constant because of the assumption. Bending moment is linearly varying in every element. So these are the solutions. In this case, since we apply external forces only at the joints, or the other way, we have one joint in every point where we have an external force, the solution is exact. Okay?
Doctor?
Yeah.
Yeah, I just have a question.
Yeah, go on.
What could happen if I have a bending moment applied on a point in the middle of an element, and I don't want to apply a shorter element that the joint construct with? So
okay.
I can
Yeah,
transform the
you can,
the
but
moment
you have to be
forces.
patient. Yeah, but you have to be patient. Okay. What you are saying is that what happens if I have not a bending moment, but an external moment here? You can transform this into forces and moments like this. And to do that, we have to apply an energy method. We're going to learn that in the next chapter. Don't worry, hold your question for a couple of weeks and we will answer that.
Okay.
Okay, but yeah, the best is to include, if you have a concentrated action, forces and moment, the best thing to do is to include a joint in that position. But if you want to save some space, you can do this and still keep working with 3 joints. But you can do that in a very elegant way. You will see that. We'll see that in the next chapter. Okay. Now let's see this. Okay. Let's suppose that we have this structure, which is a combination of these 2 elements. And we have these 2 forces like this one. Okay, of course, we see immediately that this and that, they don't have the same direction. So we have to do an analysis in the plane. Okay, so there are different ways to discretize this. This is one. Okay, so I'm defining joint element 1, which goes from here to there. So basically, this is what I'm saying is that this is my local reference system for element 1. And this is the second one, goes from 2 to 3. So this is local, and this is local. Okay, so this is theta, and this is theta. You see that for the second element, theta is negative. Or you can go in this way. It's the same. Anyway, these are the properties. Okay, this is the angle, cosine and sine, because we need that. And we need this to evaluate all of this. And this is for the second element. In this case, theta is minus 90, as we said before. This is easy because sine is 90, it's cosine is 0, sine is minus 90, so it's easier. Okay, so this is just evaluating all the. Now, what is new is that here we have inertia and sectional area. Inertia and sectional area. That means that in both elements, we're going to consider in plane and also axial and bending effects. Both effects will be considered, okay? So it's like a combination of chapter 1 and chapter 2, okay? Immediately you see, because EA is connected to aligned or inline support, and EI, inertia, is for bending. Now, this is the K matrix. This is the K matrix in the global reference system. Okay, in this case, remember, this is the first element. So you see that there is no hat because this is in a global reference system. Okay. This is again, this is the second matrix. This is K in the global reference system, but for the second element. And then we combine. This is something that we have done many times, okay? So this part here, Jesus Christ. Is for this matrix here, and this part here is from the second element. Of course, in this part, in blue, you have the combination. Now, not only that, but you see that this joint here and this joint here are completely clamped. So they cannot move, they cannot rotate. So we are going to left only with 3 displacements, 2 linear, 1 rotation, to calculate in order to solve this problem, okay? So that's something that we have seen many times. Questions about these people? Questions? No question, okay. Now.
Doctor, sorry.
Yeah, no problem.
I have a question. I can see just 2 structures, right?
I can see what? I'm sorry?
I can see just 2 structures in this figure.
No, it is a single structure. It's a single because in this part here, in the central area, you have the combination, you have the influence of both. See, in here, in this part here, you have the combination. So this value here is equal to this plus.
Right, I know, Doctor. My ask is about the structure. How many members we got?
Two. That's why this is a table of connectivity.
Okay.
See, this is element 1. Maybe I didn't write it here. This is element 1. And this is element 2. This is a connectivity table.
Okay, thank you.
No problem. If there is something which you don't get it immediately, so we don't try to solve it right there. Now, we have to solve it. Okay, so these are the supports or the boundary conditions. There are enough boundary conditions to take the singularity out. The first joint doesn't move, doesn't rotate, similarly for the third. And what we do, remember, is that we put in here and in here a large value, I'm using this, which is, I think it's large enough, right? You see that this value, for example, is 10 to the 8, but this is 10 to the 20. So it's more than 12 times, no, 12 e to the 12 times. So it is really much larger than this one, right? And on the right-hand side, what I do is I take the value of K1, multiplied by the value that I desire, which is 0. That's why I have these 3 zeros and these 3 zeros. In this case, how much is the moment, the external moment in join 2? People, external moment in join 2. Anybody?
0, I guess.
Exactly, exactamundo. That's why you see here on the external forces here, this is to the right, this is downwards, and there is no rotation. See, this is to the right, according to reference system, that's positive. This is downwards, according to a reference system, that's negative, and there's no rotation, as you said. So these are external forces, and that's it. So we're gonna take this system of equations, this 3 by 3, we take these 3, and we solve it. But as I said before, we don't need to do that. We don't need to extract that subsystem. We just do this transformation, include these large values on the left, on the right, something similar, and that's what we proceed to solve. That's the solution. And you see here on the vector that this is not 0, right? But this is the displacement of this point. How much is this? E to the minus 16. Basically 0. So this is the solution. Now, this 2 to the minus 4, that's the displacement in the x direction. So this point here moves to the right. Not much. There. That point also moves downwards, but did you see that this is much smaller amount? So this moves downwards. And also rotates. You see that if I have these forces, it will rotate like this. But that's the opposite as this one. That's why you see here that the rotation, phi2, is negative. So at the end, we're going to have something like this. This moves like this, go to that point. I'm sorry, up to here. Okay? And then this one here comes like this. Let me try to. There. Remember, this is global reference system. These are global displacement. Okay? Questions about this, people? Questions about this? Questions? Yeah, you can proceed at home and review it. The second step, remember, is to find the unknown reactions. So what you do is you multiply the vector of global displacement that you know, this vector is completely known, to multiply by the original times the original stiffness matrix, that's this one here, that's the original, and the results here, these are the reactions. So these are the reactions, and these are the reactions. These 3 are known, so we don't care. So here, I see that I need a force to the left here, This is external forces. I need a force downward, and I need a positive moment. So this is similarly on the other side. And then you have to proceed. We're going to review this to find the internal forces on each element. So these are this is the vector of displacement in the global reference system. We're going to analyze the first element, which is defined from joint 1 to joint 2. So this is the T matrix. We multiply by the D vector. So this is the displacements of the first joint. These are the displacement of the second joint, which are these three values. And the result is going to be the displacement of this element, but in the local reference system. So with this, I'm going to stop. So what we're saying is that in this case, this is the local reference system, like this. So this point here moves, we are seeing here, it moves to the right. And this is 0.000122. Moves vertically like this. And this is 0.000185. The rotation doesn't change, so it rotates like this. See, since you know that this point moves to the right, that means that this element 1, is going to be in tension. Just because of this displacement. Okay, people, is there any final questions? Any final question? Final questions? No? Okay, please start your homework right away. I don't want you to leave it for the last minute. And then we'll see you next Monday. There is no classes because this week we have 3 sessions. So we are finished with you. So I'll see you next Thursday. Okay? Have a nice and safe holidays. And some of you, I'll see you tomorrow here for the vibrations quiz. Okay, people. Bye-bye now.
Thank you, Doctor. Thank you, Doctor.
You're welcome.
Doctor, just to confirm, the lesson is at what time?
This afternoon? No, tomorrow is 1:30.
1:30 p.m.
Yeah, 1:30 p.m. At 12 at noon, we're going to have try to be earlier so we can, as yesterday, we can have a little chat, talk, laugh, share experiences and things like that. It was a very nice moment yesterday, so try to be here a little bit earlier. If you want, try something to share or try your own food so we can sit and chat and talk and laugh. Otherwise, yes, quiz will start at 1:30.